Viktor, and you can take it away. Thank you.
Thank you. And thank you to the organizers for putting together this workshop. So this talk is based on this paper, same name, Hydrodynamic Attractors in Phase Space, which is worked together with Michał Heller, Michał Spalinski, and Roe Jefferson. And in this talk, I'm going to present two different perspectives on the attractor. One perspective is from dynamical systems and the other from machine learning. And these suggest different methods for how to search for attractors. And I'm going to focus on the machine learning part, because that's what we focus on in the paper. I'm going to be looking at a few different models. There's going to be plenty of acronyms to go around. But we will focus on conformal theories and stick to Bjork and flow. So let's start with BRSSS. And the precise form of the equations of motion are not going to be very important for us. What's going to be important is how many degrees of freedom there are and how you parameterize these degrees of freedom. Now, in this setting for BRSSS, you can express it as a second order ODE for the temperature as a function of proper time. So this is 2 degrees of freedom. Now, at late times, one can solve it in a perturbative expansion. And this perturbative expansion includes one parameter, lambda, which is some remnant of the initial conditions. One can change variables and look instead at the pressure anisotropy, A, and express it as a function of another time variable, W, defined in this way. And because now it's first order, we have lost a degree of freedom. And it turns out the degree of freedom you're able to remove is precisely this lambda in the perturbative series in proper time. And something interesting happens in this choice of variables, namely you see this attractor, which you don't see for the temperature. So let's look at this attractor. So here's a plot, and there's just a bunch of solutions to the BRSSS equations for the pressure anisotropy. We can also solve this equation in a gradient expansion, which in this time variable is a late time expansion. And this expansion turns out to be completely universal. It doesn't depend on initial conditions. So every solution here converges to it at late times. But something else seems to be going on, in that they seem to converge, many of them converge earlier to something that's not this truncated gradient expansion. And one way to approximate that is what's called the slow roll. And in the slow roll, that's this red curve, and this is not a solution. This is just the union of points where the time derivative of the pressure anisotropy vanishes. And it does a little better job than the gradient expansion at early times. Even better is this attractor solution. And the way to identify this attractor solution is from the fact that it's the only one of these solutions that is finite at the initial time, at W equals 0. All of the other ones blow up. And we can make this precise with the theory of dynamical systems. What we have is a non-autonomous dynamical system. Non-autonomous just means that the equations of motion depend on time. But for these systems, there's two popular notions of attractors: the forward attractor and the pullback attractor. The forward attractor cares about what happens at late times. So a solution is a forward attractor if nearby solutions converge to it at late times. And basically every solution here is a forward attractor. On the other hand, the pullback attractor cares what happens at early times. And you find it by initializing solutions earlier and earlier. So this is a sequence of solutions initialized earlier all the way to time equals 0. And one sees that they converge to some curve. And this is the pullback attractor, which is this hydrodynamic attractor found by Heller and Spalinski. So So these are well-studied objects in the theory of dynamical systems. So one can borrow techniques and ideas from there to study this in other models. And this is a very nice approach. And you can make very sharp statements by considering these asymptotic limits of early or late times. And some of the papers that pursue this line of reasoning is to the right here. But I want to shift focus a little bit. So there are some papers that try to make the attractor useful. And they do this by exploiting the universality of the attractor to make some relation between some initial data and final data. And for such considerations, it's not strictly necessary to use these asymptotic notions. You don't have to go all the way to W equals 0. So notions like the pullback attractor are not strictly necessary. And another reason is that the early time limit is a kind of UV limit. And I'm personally a little bit uncomfortable relying too much on what happens at the UV limit. So let's try to describe what we see only using concepts at finite times. And I want to sort of look at three different terms here. So information loss, dimensionality reduction, and universality. So any experiment that you do will only probe some finite range of initial conditions. So here are two hypothetical experiments, one in orange and one in green. And for the orange experiment, you start with initial conditions with some spread in the pressure anisotropy. And as time evolves, this just shrinks, contracts. And same for the green one. So this is some kind of information loss. And eventually, this shrinks down to what and will become essentially a point. Now, when that happens, it will ultimately depend on your experimental precision when you think it's point-like. Now, there's another thing that is happening here, which is different, and that is that all of the solutions seem to end up in some region. And this will be, we will call this universality. And one way to characterize this universality is by the pullback attractor. And another way is by the slow roll, or more generally, just looking where solutions evolve very slowly so that we can define a slow region just by looking at the slope of this A, and that captures the universality pretty well. Now, I want to not rely on this pressure anisotropy to see this attractor behavior. I want to be able to see it just using the temperature, for example. But if I plot a bunch of solutions for the temperature as a function of proper time, I don't see this nice universality emerging. There's no collapse here. And of course, it shouldn't be, because at late times, there's still this parameter lambda, which distinguishes between the different solutions. But we know that the attractor behavior is still there. It's just behind the scenes somewhere. And what's going on is that we have 2 degrees of freedom, and at late times we end up with 1. So there's a 2-dimensional thing collapsing to a 1-dimensional thing. And so it's clear that we need to have another axis in our plots. So if we add in another axis here, the time derivative of temperature, you can see this phenomena, right? You have a 2-dimensional thing here, and all the solutions form a 1-dimensional thing in the end. Let's dig in a little bit deeper. So the solutions are points moving around in the phase space, parameterized by temperature and its derivative. And we normalize them so that the axes are dimensionless. And now, in order to compare distances in this space, I need to impose some metric. And we use the Euclidean metric. But you may wonder why. I mean, it's not really obvious that I should measure distances in the time derivative of temperature the same way as in the temperature. Does that make any sense? Well, it's kind of a hard question. The ultimate answer to what metric should be appropriate must in the end boil down to the experiment you're doing. And we're not doing any such analysis, so it's not, we just picked this. But we do expect that the findings are reasonably robust if you change these coordinates or change the metric. But anyway, these points, if you follow these points, this cloud of points, as time evolves, we go to the other plots, you see that it collapses from 2-dimensional to 1-dimensional. Now we've highlighted some clouds here, so the brown and blue and green clouds, to show that this behavior can be different in different parts of phase space. See, the brown cloud collapses much faster than the other ones. So this is information loss and dimensionality reduction. What about universality? Well, all of these points seem to end up in some region. That region, we can characterize it either with this background color, which just denotes the velocity of these points, or by the pullback attractor taken from the pressure anisotropy. That's the red curve. So if you wanted to use these ideas to study other theories, the basic problem is pretty clear, right? It's to identify the effective dimensionality of some set of points in some possibly high-dimensional space. And luckily, this is a well-studied question in machine learning, so we can just borrow techniques and ideas from that field. And we had some fun playing around with different algorithms, but in the end, we settled on what is perhaps the simplest technique, and that is principal component analysis, or PCA. And what this algorithm does is just, if you have a set of points, the blue points in this plane here, PCA fits an ellipsoid to this set of points. And the axes of these ellipsoid are called principal components. And each component is associated with a number called explained variance, which measures basically how much this cloud extends in that direction. So one could check for dimensionality by just comparing these principal components. If one is very small, that dimension has disappeared. And one of the main limitations of this method is that it cannot handle any curvature. So let's see what this does in BRSSS. So we do it for these three clouds here. Let's take the blue one. The blue one gives us two principal components with two explained variances, and we can follow them as a function of time. So we have the dashed blue here and the filled blue here. And they're normalized so that their sum is 1. Now they start out equal because that's how we chose our initial conditions. It was originally a circle, and then one quickly decays and becomes vanishingly small. So one can say we go from a 2-dimensional regime to a 1-dimensional regime. And the other clouds also do this, but on different timescales. And we can also check the slope. I mean, we can check how this decays. So if you take this decaying principal component and express it as a function of the W coordinate, we can compare it to the non-hydrodynamic mode in the theory. The non-hydro mode, we know that it exponentially decays with the slope of 1.5. And if you check this principal component, it decays exponentially with the slope of 3. So it's a factor of 2 faster than the non-hydro mode. But that probably just comes from the fact that we're looking at variances. So this factor of 2 is pretty natural. Now with PCA, we're not stuck with looking at figures anymore. I mean, looking at plots and seeing these shapes visually, we can actually quantify it. So we can go on to other theories. Maybe we want to include more non-hydro modes, such as in the HASW theory. We have 2 transient modes and they oscillate. So here you start out with some, so phase space is three-dimensional, and you start out in some three-dimensional regime. One of the principal components decays, you enter some two-dimensional regime, and finally one-dimensional. And since phase space is three-dimensional, we can still visually confirm that that's what's going on. Now, more interestingly is to go to kinetic theory. This is a big jump up in complexity. So in this case, the state is encoded in the one particle distribution function. And this is an infinite dimensional space, but it's naturally parameterized by the moments of this function. Now, in the RTA approximation, in Bjorkenflow, it's easy to solve for all of these moments following earlier work. And these moments are indexed by two integers, n and m, ranging from 0 up to infinity. So it's a discrete infinity, but infinity is still too much. So we just focus on the moments with n and m smaller or equal to 3. And we also normalize them by their equilibrium value. So that will be our phase space. And this is all following Strickland very closely. And he looked at these moments one by one, looked at them individually to see that they all have this attractor behavior. And what we're doing, we're not looking at them one by one, we're looking at them all at once, studying this 16-dimensional space that they move around in. So we have to define some initial distribution function, and this is it. And what's important is that it depends on 5 parameters, which means that our initial conditions is at most 5-dimensional. And differently from in the previous models, where we had great control over the initial conditions, and we're able to choose the initial conditions such that the principal components all had equal length at the initial time slice, we can't do that here. So already at the initial time, there's some separation between these explained variances. Nevertheless, if you go to some later time and go past this cusp here, you see some behavior that you would expect. So what you see is one of the components dominates, and the other ones are exponentially decaying. So the one that dominates should correspond to this parameter lambda, and the other ones correspond to some non-hydrodynamic modes. You see that the second component stabilizes after some time. And probably what's going on here is that we're running into the limitations of PCA. PCA can only capture linear stuff, and we don't expect this to necessarily be linear. So if it has some curvature, you would see something like this. If you go on to study these slopes in more detail, and we can go on to compare them with the known behavior of the transients, they all decay with a slope of 3/2. There's an infinite number of them, and they're distinguished by a subleading power law. But we will just check the slope. And if you look at the slope of the explained variance as a function of W, their decay seems to approach -3. Again, twice the decay rate of these transients. Twice coming from the fact that we're looking at the variance. So now what about universality in this case? We didn't study it, but the slow roll approximation was investigated several years ago by Romachke, and that's how we characterized the attractor back then. So this brings me to my summary slide. And so I presented 2 views on the attractor. One view is from dynamical systems. And there you talk about different well-defined notions of attractors, trans theories, and you care a lot about asymptotics. Another perspective is to use machine learning. And then you care about information loss, dimensionality reduction, and don't care so much about the asymptotics. And we used PCA, one of the simplest techniques, to quantify information loss and the effective dimensionality, check that it works in several of the models where the attractor has previously been analyzed. And we could match the decay of these components to the non-hydrodynamic modes. And this gives us one way to detect attractors without requiring some special parameterization like the pressure anisotropy. And finally, the universality is often characterized by the slow region in phase space, so generalizing the slow roll approximation. And with that, thank you.
Thank you, Victor. So I believe we have a question from Mauricio. Can you unmute yourself?
Yes, do you hear me?
Yes.
Yeah, okay, so I have a question, like I have not understood. I read your paper. When you say machine learning, what is the machine learning in this case? I don't see any learning in your machine. You are using a statistical technique very well implemented there, which is fine, but I just don't know what the machine is learning here. Can you point out this kind of aspect? Because I just don't follow.
No, that's a fair point. I mean, our machine learning isn't very sophisticated. And I suppose one could debate whether PCA is a machine learning technique or not.
It's not a statistical technique. It's not really, the machine is not learning. That's my point.
That's fine. I have no strong opinion whether you want to call it a machine learning technique or not. We use PCA, but what we want to point out is you can use other techniques from that field. We just picked the simplest one. And
but that doesn't answer my question. My question is, what is the machine learning in your course?
We use PCA. We don't do anything else. If you don't consider PCA machine learning, then we're not doing machine learning. Yeah.
You are not doing machine learning. That's what you're answering.
Okay. Yeah, sure.
Sorry, could I interject? Because I also have principal components, and I think it is fair to call it machine learning. It learns the principal components. It learns in your big data sample, which are the dominant directions of your variance. And that's what this method tells you.
Okay, so I'll take that as a comment. And then Lipe also has a question.
Yeah, can I ask a question about slide 8?
Yeah.
So it seems to me there are some points left from the brown cloud in the final time slice, and they move to the that side of the red line. So what does that mean, or why that happens?
So you mean these points here?
Yeah.
Yeah. So these are they are not part of this brown cloud here. They are just part of these other solutions.
Oh, I see.
And so you see this cloud here is cut off here because this marks a border between some instability. So there's some funny stuff happening here at the border, and I think these points are close to that border.
I see. Thanks.
Okay, we have a question from Chandra Doi.
So my question is, deviations from the attractor decay via exponential at late times. The decay is known to be power law dominated at early times. So where do you see that power law decay?
So we haven't checked the early time behavior, but at least in this plot here, for the brown cloud, it's clearly not exponential at early time. It deviates. I don't know if it's going to be power law. Maybe it should be from the theory, but we haven't checked it. And the other ones are at pretty late times.
Okay, thanks.
Travis has a question.
Thanks. Hi. I had a question. I don't know too much about the ADA-CFT side stuff, but I do have an understanding that there is somehow a way you can define entropy production in a consistent manner. So for when you have your strongly coupled system that you're doing the attractor for, is there a way that you can maybe calculate this information loss and associate it with some sort of entropy production in that system?
I have no idea, actually. It's a good question. And I think the ADS-CFT case is interesting. We didn't consider it here. One of the reasons is that we're not exactly sure what should be our phase space. In kinetic theory, it was pretty simple, right? The moment is a very natural space. In ADS-CFT, it's not clear to me what is the natural space to look at.
I see. Would you be I guess, in the framework of kinetic theory, do you think you could do it here with the stuff we got going on right now?
Right. So in order to do this, right, all you need to be able to do is to calculate solutions. You don't need to do any fancy stuff with the equations, right? If you can calculate solutions, you can just apply these techniques to it. So if you can calculate solutions and you have some phase space that you want to look at, you can just apply it.
Okay, so Soren has a question.
Yeah, hi, can you hear me?
Hi, yeah.
Yeah, good, perfect. Yeah, I was wondering about sort of the time scales that this dimensional reduction happens, right? Because there's, I mean, as was kind of pointed out in a in an earlier question, there's, so to say, different mechanisms at work. In particular, if you look at, say, kinetic theory or so. So since at late times you always see this power, this exponential decay, they're really the time scale for, so to say, dimensionality reduction and somehow losing sensitivity is set by the non-hydro mode. But I mean, the real power of something like an attractor would be to have something like that earlier, right? So I'm wondering whether you see this, or whether there's a way of quantifying when that happens within your framework.
Right. Yeah, no, so I agree that getting some well-defined timescale is basically only possible if you use the W variable and you do late time. Otherwise, it's hard to get some universal timescale. I guess what you can do is just look at these components and look at the timescale of these. Now, this will of course be different depending on the different regions of phase space you're looking at. And if you can stomach that, one can do that. But I don't have any final answer to your question.
Okay, thanks.
Okay, are there any other questions?
Will these talks be posted on the website?
I'll let an organizer who's sitting next to me answer that.
I think that's the point. Yeah, we are actually going to do that. So Mihal can confirm this, but we should be doing that. So
Victor agrees, yes.
Yes. I just have a quick question. So what happens, like, once you have more and more Knudsen numbers, right? Because so this W is like one of the Knudsen number, but of course, once the flow is complicated enough, you can have many more of these things, like something involving the sigma mu nu, something involving the bulk, or something else. Are you supposed to create then a completely multi-dimensional thing and see how it settles down? How would that be?
Right. Yeah, I mean, you should include all of the variables you think are important and just create a multi-dimensional space out of it. And then just use the methods from machine learning and look at it. And having a very high number of dimensions isn't really a problem.
Yeah, I mean, it's just that it's going to get very complicated for something that is not very symmetrical, but I think it's still possible. Something in the context of heavy ions, and you can define many, like maybe like a 10-dimensional thing would still be possible. Mm. Okay, good.
So we ended up getting slightly ahead. There is another question. Never mind. So Soren, go ahead. Oh no, sorry.
There was somebody before me.
Yeah, I see now. Yes.
Okay, thank you. Since we are looking at slide number 10, I was wondering about your remark that you're using a Euclidean metric for this phase space, right? So if you use a different metric, I guess the time when you have a change from the 2-dimensional to the 1-dimensional behavior will change. So some quantitative changes will appear. could you also think of some qualitative changes that could happen?
Yes. Yes, it can change completely. So if I take this t dot axis, we normalized it here with the initial time squared. But suppose I instead took the time and I multiplied it with some maybe exponential function of the time, I would be stretching out this direction much faster than the expansion, than the contraction contracts it. So indeed, you can do, depending on the metric, you can get any result you want, actually. So I want to emphasize that choosing a metric and having a motivated choice, it's important if you want to trust your result. Although, I mean, I presented the sample with an exponential thing, and that's kind of what you have to do in order to get rid of this phenomena. So I think if you made a choice and I made a choice, we would probably see something similar, although quantitatively different.
Okay, that is somehow good to know that it's somehow reliable. Thank you.
All right, and Soren has another question.
Yeah. Okay. So this is actually a very practical question, so to say. So if you look at like a simple problem like Bjorken flow, right? I'm just wondering how many of these simulations do you actually need to kind of quantify this? Quantify this. Do your physical component analysis and quantify the dimensionality reduction, really. Because I mean, in your case, the simulation is like super cheap, right? But say you do kinetic theory for QCD or so, that actually. That's actually much tougher, so I'm curious.
Yeah, no, that's a good question. I don't know if I have any numbers in my head about how many solutions. I mean, I think we definitely have far too many solutions than what you need.
But like order 100, order 1,000, order 1,000,000, something like this.
No, I think, I mean, this is a two-dimensional phase space. So in principle, if I had 3 points, I can already do something. Is it going to be accurate? I'm not sure. But it's like, it's on the order of your dimensions of your phase space, I would think.
Yeah, sure. Yeah.
Okay, are there any other questions? All right, if not, we're running now actually a little